James Webb is a revolutionary piece of technology, providing us with unprecedented insights into the mysteries of the universe. But while James Webb peers into the farthest reaches of the cosmos, uncovering the universe's oldest and most distant secrets, it's important to remember that some of the greatest mysteries are closer to home. At an average of 238,855 miles away from Earth, which is about 30 Earths away, the Moon may be Earth's closest neighbor, but there are still countless mysteries surrounding the rocky world. NASA has spent decades researching the Moon, even landing 12 of its astronauts there. But some answers still elude its top space scientists. Like NASA scientist Robin Brett, one of the first to study and direct research on lunar samples, popularly known as moon rocks, from the Apollo space missions once said, "It seems easier to explain the non-existence of the Moon than its existence." To add to the intrigue, measurements of its gravitational field have revealed a massive, mysterious structure hidden beneath the surface on the far side, sparking a flurry of wild speculation. Could this colossal anomaly be the remains of a long-lost lunar civilization? Or is there a more plausible explanation for this lunar enigma? All this and more will be discussed in today's episode. When we gaze at the Moon from Earth, one striking fact stands out. We always see the same face. This isn't because the Moon isn't rotating. Rather, it's due to a phenomenon called synchronous rotation. The Moon takes about the same amount of time to complete one rotation on its axis as it does to orbit Earth, approximately 27.3 days. This synchronization is no coincidence, but is intricately linked to Earth's strong gravitational pull, which has exerted a tidal influence on the Moon over billions of years. This tidal locking ensures that one hemisphere, known as the near side, always faces Earth, while the opposite hemisphere, called the far side, perpetually faces away. This alignment divides the lunar surface into two distinct hemispheres: the familiar near side, visible to us, and the far side, hidden from direct view until the advent of space exploration. Anyone who has marveled at the full moon's glowing presence in the night sky is acquainted with the near side's most prominent features. Its surface showcases a fascinating contrast. Large, dark, roughly circular patches known as Maria, set against brighter highland terrain. Ancient astronomers mistook these dark regions for vast seas, dubbing them Maria, Latin for seas, because they appeared to shimmer like water under the earthbound gaze. However, we now know that these features are not liquid, but solidified plains of basaltic lava, remnants of volcanic activity that occurred billions of years ago when molten rock erupted from beneath the Moon's crust. The near side's brighter areas, known as highlands, are markedly different. They consist of older, heavily cratered terrain that is more reflective due to their composition. These highlands rise above the Maria, creating a rugged, complex landscape. For centuries, astronomers assumed that the Moon's far side would mirror the near side's features, perhaps with slight variations. It wasn't until humanity's foray into the space age that this assumption was dramatically overturned. In 1959, the Soviet Union's Luna 3 spacecraft captured the first images of the Moon's far side, revolutionizing our understanding of our celestial neighbor. Although the photographs were grainy by modern standards, they revealed a startlingly different landscape. Unlike the near side, the far side lacked sprawling Maria and was instead dominated by rugged highlands. The Maria were reduced to a few isolated dark spots scattered across the far side. These initial observations raised many questions about why the two hemispheres were so dramatically different. Decades of subsequent observations only deepened the mystery. Data from NASA's Gravity Recovery and Interior Laboratory, GRAIL mission, which used twin lunar orbiting spacecraft to map the Moon's gravitational field, revealed a significant disparity between the two hemispheres. The far side's crust was found to be about 20 kilometers thicker on average than that of the near side. This discovery suggested that the dichotomy between the hemispheres was not merely superficial, but extended deep into the moon's structure. But why did this stark difference exist? Scientists initially speculated that Earth's tidal forces might have played a role, but further investigation suggested a more complex origin. To understand this puzzle, we must look back to the moon's formation, which is best explained by the widely accepted giant impact hypothesis. According to this theory, the moon was born from a cataclysmic collision between the early Earth and a Mars-sized protoplanet named Theia. This event, occurring around 4.5 billion years ago, was a monumental turning point in the history of our planet and its satellite. The impact released an immense amount of energy, vaporizing Theia and much of Earth's outer layers. The debris from this collision, composed of molten rock and metal, was ejected into orbit around Earth. Over time, this material coalesced to form the moon. The details of the moon's assembly remain a topic of scientific debate, but researchers generally agree that this process was relatively rapid, potentially occurring within a few months to a few years. At that time, the moon was much closer to Earth than it is today, perhaps only 1/10 of its current distance. Over billions of years, tidal interactions between Earth and the moon have caused the moon to gradually drift away, a process that continues to this day at a rate of about 3.8 centimeters per year. During its early history, the young moon was still molten, and its proximity to Earth played a crucial role in shaping its features. The tidal forces between the two bodies were intense, quickly locking the moon's rotation so that one side permanently faced Earth. However, this tidal locking occurred before the moon's crust had fully formed and solidified, ruling out Earth's gravitational influence as the primary cause of the hemispheric differences. Instead, scientists hypothesized that some other process must have affected the moon's cooling and crust formation. Several theories emerged over the years to explain this mystery. One idea suggested that a second, smaller moon might have formed from the debris of the giant impact and later collided with the primary moon at a low velocity. This hypothetical collision could have deposited additional material on the far side, thickening its crust. Another possibility was that internal processes within the moon, such as convection currents in its molten interior, might have caused asymmetrical cooling and crust formation. Regardless, none of these explanations fully accounted for the observed differences. In 2014, a groundbreaking study proposed a new and compelling explanation. The far side's thicker crust may have been a direct consequence of Earth's proximity during the moon's early evolution. At that time, Earth loomed large in the lunar sky, occupying a vast 40-degree arc and radiating intense heat. The giant impact that created the moon would have left Earth's surface molten or vaporized, with temperatures reaching around 2,000 degrees Celsius. This heat radiated toward the near side of the moon, raising its temperature to about 1,000 degrees Celsius. Meanwhile, the far side, shielded from Earth's direct radiation, cooled much more rapidly. This temperature gradient had profound implications for the moon's development. During its molten phase, the moon's near side would have retained a churning atmosphere of vaporized rock and metal, while the far side allowed these elements to condense. Certain elements like calcium and aluminum have high boiling points and would have remained gaseous on the hotter near side. However, on the cooler far side, these elements condensed and interacted to form lightweight minerals, such as feldspar, which floated to the surface and contributed to the thickened crust. Indeed, modern orbital surveys have confirmed a higher concentration of feldspar on the far side compared to the near side. Additionally, the concentration of radioactive elements on the near side could have provided localized heating, promoting volcanic activity. This heating allowed magma to rise and flood the near side's surface, creating the extensive maria that dominate its landscape. In contrast, the far side, lacking significant volcanic activity, remained mostly highland terrain. While this hypothesis offers a compelling explanation for the moon's dichotomy, it is not the final word. As with any scientific theory, further evidence is needed to fully validate it. And James Webb may provide some clues. The James Webb Space Telescope is approximately 100 times more powerful than the Hubble, offering a window into the universe's mystery. While the Hubble collects visible light, ultraviolet light, and a small portion of infrared light, Webb is primarily designed to observe in the infrared spectrum. This distinction, though seemingly technical, is transformative. Infrared light has longer wavelengths than visible light, which allows it to penetrate cosmic dust clouds and reveal objects obscured from view in visible light. Moreover, infrared observations are crucial for studying ancient distant galaxies and exoplanets. Infrared light is particularly significant because of a phenomenon known as redshifting. As space expands, light traveling through it gets stretched, increasing its wavelength and shifting toward the red and infrared parts of the spectrum. Light emitted billions of years ago from stars or galaxies may have initially been in the visible spectrum, but by the time it reaches Earth, it has stretched into the infrared. The Webb telescope is designed to detect this ancient light, allowing scientists to look back over 13 billion years to study the early universe's formation and evolution. A practical analogy for redshifting is the Doppler effect, which you've likely experienced when a siren passes by. Its pitch rises as it approaches and drops as it moves away. Similarly, as objects in space recede due to the universe's expansion, their light shifts to longer wavelengths. This ability to observe redshifted light is why Webb can detect some of the oldest structures in the cosmos, unveiling a universe that existed shortly after the Big Bang. In addition to studying the early universe, Webb excels at investigating exoplanets, planets outside our solar system. Earth itself provides a key example of why infrared is crucial for this type of research. If an extraterrestrial observer were studying Earth, they would find that its peak light emission falls in the infrared spectrum due to the planet's surface temperature. This means that observing Earth-like planets around distant stars requires the capability to detect infrared radiation. Webb can analyze exoplanets' atmospheres by examining the light that passes through them during transits in front of their host stars. This process, known as transmission spectroscopy, can identify chemical signatures such as water vapor, methane, or carbon dioxide, potential indicators of habitability or even life. Webb's infrared capabilities make it uniquely suited for this task, offering unparalleled precision in detecting faint signals from these distant worlds. But in addition to unraveling the mysteries of the distant cosmos, closer to home, researchers using James Webb are uncovering intriguing possibilities for future human habitation on the moon. Recently, scientists discovered a cave on the lunar surface, part of a potentially vast network of hidden tunnels formed by ancient lava flows. This cave, estimated to be over 100 meters deep, has sparked excitement as a potential site for a permanent human base. Such a structure would protect astronauts from harsh space radiation, extreme temperatures, and micrometeorites, offering a natural refuge for long-term habitation. Interestingly, this cave, like others on the moon, might be visible to the naked eye from Earth. Located in an area that includes the Apollo 11 landing site, the cave features a skylight that opens to a vertical drop with overhanging walls and a sloping floor that may lead to further underground tunnels. These features suggest a geological history tied to the moon's volcanic past, with lava flowing beneath the surface and hollowing out tunnels millions or even billions of years ago. The closest terrestrial analogues are volcanic caves found in places like Lanzarote, Spain, which offer insights into their lunar counterparts. Although the cave has yet to be fully explored, researchers envision using technologies such as ground-penetrating radar, robotic explorers, and cameras to map its interior. Understanding these caves could provide critical information for future lunar missions, including the Artemis program, which aims to establish a sustainable human presence on the Moon. These efforts align with the broader goal of expanding human exploration to Mars and beyond. The exploration of lunar caves holds implications for investigating similar structures on Mars. On the Red Planet, caves offer a tantalizing prospect for finding evidence of past or even present microbial life. Unlike the surface, which is bombarded by intense radiation and experiences extreme temperature fluctuations, caves provide a sheltered environment. Any evidence of life on Mars, if it ever existed, is most likely preserved in these subterranean habitats, protected from the planet's harsh conditions. Studying lunar caves could serve as a testbed for future Martian exploration. The technologies and methodologies developed to explore and potentially inhabit moon caves could be adapted for use on Mars, where such environments may hold secrets about the planet's history and its potential for habitability. The implications are profound. Uncovering signs of life on Mars would reshape our understanding of biology, evolution, and the conditions required for life to thrive. Beyond their potential as habitats, lunar caves may help answer fundamental questions about the Moon's and the solar system's history. Rocks within these caves are less exposed to space weathering processes, such as micrometeorite impacts, solar wind, and cosmic radiation, which erode and alter the Moon's surface over time. This preservation means that the geological record inside caves could extend billions of years into the past, offering a pristine archive of the Moon's formation and evolution. By studying these untouched samples, scientists could gain insights into the processes that shaped the Moon, including its volcanic activity and the impacts that created its craters. Such research would also enhance our understanding of Earth's early history, as the Moon and Earth share a common origin in the aftermath of a colossal collision with a Mars-sized body around 4.5 billion years ago. Fascinatingly, besides the Moon, the Webb telescope is also setting its sights on a more elusive class of celestial objects, moons beyond our solar system. These are known as extrasolar moons, or exomoons. While the concept of exomoons has long captured the imagination of astronomers and science fiction enthusiasts alike, the reality of detecting these tiny worlds has proven to be far more challenging than discovering their larger counterparts, exoplanets. This difficulty arises from the fundamental techniques used in the hunt. Astronomers primarily detect exoplanets using the transit method, a process that involves observing the dimming of a star's light as a planet passes, or transits, in front of it. This technique relies on measuring minuscule changes in the brightness of a star, caused by the planet blocking a fraction of its light. However, even for large exoplanets, the change in brightness can be incredibly subtle. When it comes to detecting exomoons, the challenge grows exponentially. Unlike exoplanets, which can block a significant amount of light due to their larger sizes, exomoons are far smaller and block much less light. Furthermore, their detection requires precise timing. An exomoon must be in the exact position to transit alongside its host planet when it crosses the face of its star. If this alignment doesn't occur, the exomoon remains invisible to our instruments. The faint light dip caused by an exomoon would be so minute that it could easily be overlooked or mistaken for noise in the data. Scientists must also contend with the fact that an exomoon's signal is often entangled with that of its host planet. This makes disentangling the two an incredibly intricate process, requiring advanced instruments and techniques. To identify an exomoon, astronomers rely on reverse calculations. By carefully analyzing the light curve, the graph showing how a star's brightness changes over time, they can deduce whether the observed dimming was caused by an exoplanet alone or if an exomoon also contributed to the light obstruction. Despite these challenges, the James Webb Space Telescope's advanced capabilities offer new hope in the quest to identify these elusive celestial bodies. Equipped with the near-infrared imager and slitless spectrograph, or NIRIS for short, Webb is uniquely positioned to make the first undisputed detection of an exomoon. NIRIS allows scientists to observe stars and planets with unprecedented precision, capturing even the faintest signals that might betray the presence of an orbiting moon. Such a discovery would mark a pivotal moment in the study of planetary systems beyond our own, opening the door to entirely new avenues of research. If confirmed, exomoons could reshape our understanding of planetary systems. These moons may hold clues to the processes of planet formation and the dynamic interactions between planets and their satellites. Some researchers even speculate that certain exomoons could harbor conditions suitable for life, making them prime targets in the search for extraterrestrial habitats. This emerging field of study, often referred to as the exomoon revolution, promises to unveil secrets about the diversity and complexity of planetary systems across the universe. While the hunt for exomoons is still in its infancy, Webb's mission goes far beyond these objects. A significant portion of its current research focuses on the exoplanets themselves, particularly those that might possess the conditions necessary for life as we know it. One such project, part of Webb's Cycle 3 General Observers, also known as GEO program, aims to study the atmosphere of TOI 44481b, a terrestrial exoplanet. This project will utilize Webb's MIRI for 16 hours to analyze the planet's atmosphere and determine whether it has managed to retain its gaseous envelope. TOI 4481b is particularly intriguing because it orbits an M-type star, also known as a red dwarf, which is about half the mass of the Sun and located roughly 39 light-years away. The significance of this study extends beyond TOI 4481b itself. Understanding whether rocky planets around red dwarfs can retain substantial atmospheres is critical for assessing their potential habitability. Red dwarfs are the most common type of star in the Milky Way, making them likely hosts for many of the galaxy's terrestrial planets. However, their intense stellar activity, including frequent flares and high levels of radiation, often poses challenges for the survival of planetary atmospheres. By studying TOI 4481b, scientists hope to gather data that could serve as a stepping stone toward determining the habitability of other planets orbiting red dwarfs. This research is vital for answering one of humanity's most profound questions. Are we alone in the universe? But the James Webb Space Telescope's capabilities extend far beyond exoplanets and their moons. Another exciting frontier of its exploration is the study of supermassive black holes, some of the most enigmatic and powerful objects in the universe. Astronomers have long theorized that nearly every large galaxy harbors a supermassive black hole at its center. These cosmic giants can have masses ranging from millions to billions of times that of the Sun. Some are relatively quiet, lying dormant at the hearts of galaxies, while others are extraordinarily active, consuming vast amounts of gas and dust from their surroundings. These active supermassive black holes are often surrounded by accretion disks, swirling disks of material that are heated to extreme temperatures as they spiral toward the black hole's event horizon. The immense gravitational forces exerted by these black holes cause the material in the accretion disks to emit intense radiation across the electromagnetic spectrum. When these black holes are actively feeding, they can create phenomena known as active galactic nuclei, or AGN. AGNs are among the brightest objects in the universe, capable of outshining the combined light of all the stars in their host galaxies. In some cases, the black hole's activity leads to the formation of powerful jets of particles, which are ejected at nearly the speed of light from the poles of the accretion disk. These jets can extend for thousands of light years and are responsible for creating quasars, which are some of the most luminous and energetic events in the cosmos. The study of AGNs and quasars is not only fascinating, but also crucial for understanding the evolution of galaxies. The violent processes associated with these phenomena influence their host galaxies in profound ways, regulating star formation and shaping their overall structure. Webb's advanced instruments are perfectly suited to study these extreme environments. By observing the light emitted by AGNs and quasars across various wavelengths, Webb can provide insights into the behavior of matter under the influence of intense gravitational forces. This will allow astronomers to refine their models of how supermassive black holes interact with their surroundings. The significance of studying supermassive black holes was highlighted in 2019 when the Event Horizon Telescope, or EHT, captured the first-ever image of a black hole. This groundbreaking observation revealed the supermassive black hole at the center of the galaxy Messier 87, showcasing the shadow cast by its event horizon against the glowing accretion disk. While EHT provided a snapshot of a black hole's immediate environment, James Webb aims to delve deeper into the broader implications of these objects. Its Cycle 3 missions include projects designed to study the connections between AGNs, their host galaxies, and the larger cosmic web. Moreover, Webb's observations could shed light on the mysteries surrounding the formation of supermassive black holes themselves. How did these colossal objects grow to such immense sizes so early in the universe's history? Did they form through the collapse of massive stars, or did they grow through the merger of smaller black holes? By peering into the distant past and observing galaxies and black holes as they appeared billions of years ago, Webb can help answer these fundamental questions. In addition to its groundbreaking studies of exomoons, exoplanets, and supermassive black holes, James Webb is making strides in a wide range of other fields. From investigating the atmospheres of distant worlds to probing the origins of the first galaxies, the telescope's capabilities are redefining our understanding of the cosmos. Each discovery brings us closer to unraveling the mysteries of our universe and finding our place within it. As James Webb continues its mission, it is clear that we are entering a new era of astronomical exploration. The search for exomoons, the study of exoplanet atmospheres, and the investigation of supermassive black holes are just a few examples of how this extraordinary observatory is pushing the boundaries of human knowledge. Whether it's uncovering the secrets of distant worlds or shedding light on the most powerful forces in the universe, James Webb is poised to transform our understanding of the cosmos for generations to come. While James Webb capabilities are impressive, there are still significant limitations. Its primary focus is infrared astronomy, which is critical for studying distant objects that have emitted light in the infrared spectrum due to the expansion of the universe. However, many questions in astronomy require observations across different wavelengths of light. The next generation of telescopes is expected to complement and expand upon the capabilities of James Webb by covering a broader range of wavelengths, including ultraviolet, visible, and even radio frequencies, as well as enhancing the resolution, sensitivity, and observational depth. Here is a quick look at some next-generation telescopes after James Webb. Number 1. The Nancy Grace Roman Space Telescope. The Nancy Grace Roman Space Telescope, slated for launch in the mid-2020s, is one of the most highly anticipated next-generation space telescopes. Developed by NASA, this telescope is designed to complement the capabilities of James Webb by offering wide-field imaging capabilities in the infrared and visible wavelengths. One of its main goals is to provide detailed data on dark energy and dark matter, two of the most mysterious components of the universe. The Roman Space Telescope will be equipped with a 2.4-meter aperture, similar to the Hubble Space Telescopes, but it will have a much wider field of view, capable of surveying areas of the sky thousands of times larger than Hubble. This will allow it to conduct large-scale surveys of galaxies, supernovae, and the cosmic microwave background, enhancing our understanding of dark energy, the force responsible for the accelerated expansion of the universe. Roman's wide-field imaging capabilities will also enable it to carry out an exoplanet survey, hunting for these planets by detecting small dips in starlight caused by the passage of a planet across the face of its star. It will focus on investigating exoplanet atmospheres, potentially identifying the chemical signatures of life in distant worlds. One of the most powerful aspects of the Roman Space Telescope is its ability to work in tandem with James Webb. While the Webb telescope focuses on high-resolution infrared observations, Roman will offer complementary wide-field surveys in visible and infrared wavelengths. This synergy will enhance our understanding of the universe by providing both detailed and large-scale views of astronomical phenomena. Number 2. The Luvoir Mission. The Luvoir Mission is a proposed multi-wavelength space observatory that would operate across the ultraviolet, optical, and infrared spectrum. Luvoir is being designed to be one of the most ambitious telescopes to date, and it is considered a potential successor to the Hubble Space Telescope and James Webb. Luvoir is expected to have a massive primary mirror, with the size ranging from 6 meters to 15 meters in diameter. The large mirror would give Luvoir unprecedented resolution and sensitivity. With this capability, Luvoir would study everything from exoplanets to star formation, galaxy evolution, and the search for life beyond Earth. Luvoir's key objective is to study exoplanets in detail, including their atmospheres. It would use advanced techniques such as direct imaging and spectroscopy to identify Earth-like planets in the habitable zone of stars and analyze their atmospheric composition. Luvoir could potentially detect biomarkers, signs of life, on these distant planets, transforming our understanding of habitability in the universe. However, the Luvoir mission is still in the early stages of development, and it will require significant investment and technological advancements to become a reality. Given the technical complexity and cost, Luvoir may not launch until the late 2030s or 2040s, but it promises to be one of the most transformative space telescopes when it does. Number 3. The Habex Mission. The Habex Mission is another proposed next-generation space telescope that is designed specifically to search for habitable exoplanets and study their atmospheres for signs of life. Unlike other telescopes that focus on distant galaxies or large-scale cosmology, Habex's primary focus would be on directly imaging Earth-like planets in the habitable zone of other stars. Habex would feature a large 4-meter primary mirror and would be equipped with a coronagraph, a device that blocks the light from stars while allowing faint light from exoplanets to be detected. This would allow Habex to directly observe exoplanets with high resolution, a technique that has been difficult to achieve with current telescopes. The primary goal of Habex would be to characterize exoplanets' atmospheres and search for biosignatures such as oxygen, methane, and carbon dioxide, which could indicate the presence of life. Additionally, Habex would study the conditions necessary for life to thrive on other worlds, potentially finding Earth-like planets that could be home to life. Number 4. The Origin Space Telescope. The Origin Space Telescope is another ambitious concept for a next-generation space telescope, designed to study the origins of the universe and the formation of stars and galaxies. With its cutting-edge infrared capabilities, Origins would complement James Webb and provide deeper insights into the early universe. The Origin Space Telescope is expected to launch sometime in the 2030s or 2040s, and its long-term vision would provide a deeper understanding of the cosmic processes that led to the formation of galaxies, stars, and planetary systems. Its contributions could help address fundamental questions about the evolution of the universe and the potential for life elsewhere. The next generation of space telescopes, building on the legacy of James Webb, is set to revolutionize our understanding of the universe. As these next-gen telescopes prepare for launch, they promise to carry on the work begun by James Webb and open up entirely new frontiers in astronomical exploration.
Okay, retro, go. Vital, go. Guide, go. Control, go. Telcom, go. GNC, go. Econ.
While the moon has always been an object of wonder and scientific interest to humanity, lunar exploration began in earnest in the 1950s, with the United States and the USSR developing and launching robotic spacecraft. In 1959, the USSR's Luna 1 was the first spacecraft to fly by the moon. In 1966, Luna 9 achieved the first soft landing, and in 1969, the US's Apollo 11 achieved the first human landing. In the decades since, many nations have contributed to lunar orbiters and landers. As of January 2024, 5 nations have successfully landed on the moon. But despite the incredible achievements, there was one aspect of the moon that remained out of reach: the far side. The far side of the moon has a certain mystique about it. It's eternally out of view, never facing the Earth, which has earned it a misleading nickname, the dark side, as if sunlight never reaches its surface. It's the section of the moon we'll never see for ourselves, not unless we hop on a spaceship and fly over there. But now, thanks to the James Webb Space Telescope, we can finally see what lies beyond the horizon, unlocking a new era of lunar exploration and discovery. Join us as we explore the mysterious realm of the moon's dark side, uncovering obscure details and highlighting our celestial neighbor's lesser-known features. Some people see a face in the moon, others see a rabbit or a toad. But regardless of what you see on the lunar surface, we all view the same side of our natural satellite. So, why don't we ever see the far side of the moon? To know why, let's look more closely at its relationship to Earth. The moon orbits in such a way that one rotation takes just about the same length of time as it takes for it to orbit around Earth. That is, the moon spins on its own axis once during its orbit around our planet. That leaves one side facing us during its orbit. The technical name for this spin-orbit lock is tidal locking. Of course, there is literally a dark side of the moon, but it's not always the same side. What is darkened depends on which phase of the moon we see. During a new moon, the moon lies between Earth and the sun. So the side we normally see from here on Earth that's normally lit by the sun is in its shadow. Only when the moon is opposite from the sun do we see that part of the surface lit up. At that point, the far side is shadowed and is truly dark. The far side of the moon was once mysterious and hidden. But that all changed when our first glimpse of the mysterious far side came early in the space race, courtesy of the Soviet Union's Luna 3 spacecraft almost 60 years ago. In 1959, barely 2 years after placing Sputnik 1 in orbit, Russian engineers managed to send the spacecraft, which was crude by today's standards, into orbit around the moon, and for the first time, we got a good look at the mysterious far side. Luna 3 took 29 film images of the far side in total, which were photographically developed, fixed, and dried on board. Remember, this was long before multi-megapixel cameras. Ironically, the film used had been stolen from American spy balloons, as it had to be sturdy and radiation-hardened. The spacecraft, using a combination of 2 camera systems, one wide field and one narrow field but higher resolution, and a crude onboard scanner, could then transmit the processed images, which were spot-scanned from the photographs, back to the receiving station in the former Soviet Union. Although only 17 of the 29 taken were transmitted successfully back to Earth, of which 6 were considered good enough for publication, they proved to be a revelation. Those 6 images covered 70% of the far side and opened a whole new perspective on the lunar surface. It was almost immediately evident that the dark patches that make the face of the man in the moon on the near side are almost completely absent on the far side. These dark patches are basaltic plains called mare, created by volcanic activity on the moon billions of years ago. Instead, the far side was littered with craters, even more so than the near side, and some of those craters were the size of small countries. The Soviets started naming many of the features they were seeing for the first time, an act which caused some controversy in what was known as the height of the Cold War era. We already had an inkling of one of those vast new craters, which is actually one of the very few mare on the far side. The subtlest hint of Mare Orientale, one of the largest impact craters known, seen on the limb of the moon, had been known of since its discovery by Julius Franz in 1906, and can be seen during good librations when that portion of the moon swings around towards us. The view from Luna 3 showed how vast an impact crater Orientale was, resembling a bullseye. It was almost 900 kilometers across, pretty much the length of the United Kingdom, give or take, and was caused by an asteroid impact, thought to be around 64-kilometer wide just under 4 billion years ago. The resulting giant crater, termed an impact basin, was subsequently filled with volcanic lava. In 1965, another Soviet mission, Zond 3, flew by the moon with a far better camera than Luna 3 possessed, and with the ability to conduct more detailed science observations, including spectroscopy. Zond 3 produced 23 very detailed photographs of the lunar far side, which enabled one of the first detailed maps of the entire lunar surface to be constructed. In the meantime, NASA was progressing its Apollo program at a phenomenal rate. Following the declaration by President Kennedy that the U.S. would place a man on the moon and return him safely to the Earth by the end of the 1960s, by December 1968, NASA was ready to send 3 people, including Frank Borman, Jim Lovell, and Bill Anders, all the way around the moon and back for the Apollo 8 mission. They became the first humans in history not only to escape from low Earth orbit, but also to see the elusive far side. This is how Lovell famously described the lunar surface. The moon is essentially gray, no color, looks like plaster of Paris or sort of a grayish beach sand. We can see quite a bit of detail. There's not as much contrast between that and the surrounding craters. The craters are all rounded off. There's quite a few of them. Some of them are newer. Many of them look like, especially the round ones, look like they were hit by meteorites or projectiles of some sort. When the Apollo 8 spacecraft flew around the far side of the moon, the signal to Earth was cut off for around 10 minutes. This loss of signal was a daunting time for the flight crew and mission control. Apollo 8 was alone and truly cut off from Earth, venturing where no human had ever gone before. As the astronauts came back around from the far side, a collective sigh of relief was breathed by many of the flight team at Mission Control in Houston. Charlie Duke, who was the lunar module pilot on the Apollo 16 mission, describes what it was like to be flying over the far side of the moon. In the words of Charlie, "The computer told us that we were out of contact with the Earth and that we had loss of signal. Then, all of a sudden, there was the sunrise. It was the most dramatic sunrise I've ever seen. In Earth orbit, you see the sun's glow on the horizon or the planet's atmosphere, and it gets brighter and brighter. The moon is different, though. There's instant sunlight with long shadows on the lunar surface. The far side of the moon was very rough back there. I would not have wanted to land on the backside of the moon." After the success of Apollo 8, Apollo 9 went back to vital low Earth orbital testing of the lunar module. So the next astronauts to visit the far side were Gene Cernan, John Young, and Tom Stafford, on board Apollo 10 in May 1969, just 2 months before the historic landing of Apollo 11. However, while flying over the far side of the moon, the trio of astronauts encountered something strange, which in the last few years NASA has been forced to re-explain thanks to conspiracy theory documentaries airing on US television. The facts had been well known since the 1970s. These strange events on Apollo 10 were manifest in the form of some very odd sounds. The radio systems on board the Apollo spacecraft were crude by modern standards, though state-of-the-art at the time. The command and lunar modules were relatively noisy environments, according to most of the astronauts, with bumps and bangs combined with the whirring of fans and engine noise. What the Apollo 10 crew heard through the radio systems baffled them. They described it as being almost like that made by an electronic instrument called a theremin, often used in creepy science fiction B-movies of the 1950s and 60s, as well as on the Beach Boys' song Good Vibrations. Research has since proven that the sound was nothing more than an interference effect from those 1960s radio communications systems on board. With the onset of the moon landings, 2 astronauts would travel to the surface, while a third remained on board the command module to orbit the moon alone, though all of them got chance to orbit the moon and see the far side before landing. The solo orbital journeys of Michael Collins, Apollo 11, Dick Gordon, Apollo 12, Stuart Roosa, Apollo 14, Al Worden, Apollo 15, Ken Mattingly, Apollo 16, and Ron Evans, Apollo 17, who were the unsung heroes of the Apollo missions, are some of the bravest feats ever achieved by astronauts. They would spend days making quite detailed lunar observations from orbit, mapping features nobody had ever seen before. Al Worden is often quoted as saying that his time alone was some of the best he had during the Apollo 15 mission. According to Al Worden, the far side, the views at certain times when the sun and the earth are blocked out, are like nothing you could imagine. The sheer number of stars you see is incredible. It's like a sheet of white, and you know that every single one of them is a sun in its own right. A question often asked of the Apollo astronauts and flight teams is, why were all the missions just to the near side? In fact, the answer is so simple. As Charlie Duke says, we wanted to be in contact with the Earth, so we weren't able to land on the far side of the moon. Should something have gone wrong while the astronauts were on the surface, they would not have been able to communicate directly with Earth. This would not be such a problem today, as satellites could be put into lunar orbit to relay communications. The far side is of growing interest to scientists and potentially future planned human missions. Indeed, the possibilities for the far side of the moon are vast. For many decades, the astronomical and scientific community has wanted to put radio telescopes and optical telescopes on the far side. Observatories on the far side would be shielded from not only man-made radio interference from Earth, but also the glare of daylight on our planet. The telescopes could be built inside craters to avoid solar radiation, and would provide us with an unprecedentedly clear insight deep into the far reaches of the universe. Otherwise, we also have little true understanding of the processes that make the far side so vastly different in appearance to the near side. Thus, with NASA gearing up to send astronauts to the moon's south pole, there's never been a better time to be a lunatic. The surge of interest in lunar exploration is great news for planetary scientists, hoping to learn more about Earth's rocky sidekick. These are the burning questions they're dying to find the answers to. According to Noah Petro, a research scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and a project scientist for the Lunar Reconnaissance Orbiter, the fundamental question of how the moon formed and how that relates to the Earth is really the most important of the unknowns. Everything else comes after that. You can thank Apollo 11 for giving us our first insight into that mystery. The mission brought back 50 pounds worth of moon rocks and initiated decades of investigations focused on learning how the moon formed and evolved. Scientists used them to come up with the strongest existing model, that the moon began as a magma ocean, a giant ball of molten lava orbiting Earth. This in turn led decades later to the hypothesis that the moon was born out of Earth itself, when a giant impact with a Mars-sized object ejected debris into orbit. Further studies of the rock show the material that formed the moon also formed our own planet, adding more support to this idea. That's the most widely accepted hypothesis for the origin of the moon, but it's by no means perfect. There is no way yet to confirm a giant impact created the moon, and our sense of how the magma ocean cooled down into the dry, gray rock we see now is still very hazy. About 10 years ago, we discovered evidence of water on the moon, something that's a bit difficult to reconcile with an impact hypothesis. Getting to the bottom of the moon's past requires the sort of on-the-ground work we've done to unravel Earth's own history. Put the origin of the moon aside, Apollo moon rocks continues to challenge our understanding with another conundrum. Why aren't moon rocks as old as the moon? The moon is just over 4.5 billion years old, which makes it a mere 60 million years younger than the solar system itself. The early days of the inner solar system were chaotic and defined by the constant collision of solid materials as they whipped around the nascent sun, gradually forming larger and larger bodies in a process known as planetary accretion. Analysis of the rocks collected by the Apollo astronauts shows that most were created by impact events about 3.9 billion years ago, but almost none of them were dated to the moon's first 600 million years of existence. This is weird because impact events should have become less frequent as the planetary accretion process wound down, so you'd expect to find a lot more rocks formed from earlier collisions. This led scientists to hypothesize that the moon was subject to intense collisions about 3.9 billion years ago, a period known as the Late Heavy Bombardment, or more poetically, the Lunar Cataclysm. While this theory nicely accounts for the Apollo moon rocks, it also raises a big question. What caused all these rocks to start pummeling the moon? The leading model suggests that the outer planets used to orbit much closer to the sun, and as they moved outward, sent big rocks on a collision course with the moon. But an alternative theory posits that the cataclysm never happened and that the preponderance of rocks dating to 3.9 billion years ago is due to sample bias. The last 3 Apollo missions all took samples from 3 major impact craters: Imbrium, Serenitatis, and Nectaris. New evidence suggests that the samples used to date the age of each of these craters, which is crucial to determining whether a period of heavy bombardment occurred, may actually just be debris from the impact that formed the largest crater, Imbrium, about 3.9 billion years ago. So, the best way to settle the lunar cataclysm debate will be to visit craters where samples aren't likely to have been contaminated by the Imbrium impact, such as the South Pole or the far side of the moon. If most of those new samples are older than 3.9 billion years, it will cast the theory of the lunar cataclysm in serious doubt and also help scientists better understand conditions in the early solar system. Regardless, interest in the lunar South Pole as a landing site is mainly driven by the fact that scientists know the region hosts lunar water. Indeed, there's water on the moon, and NASA first found water on the moon in 2009. But we're not just talking about a little sprinkling of interstellar water. We're talking about troves and troves of water ice that could be sitting just beneath the surface, especially at the lunar poles. This is good news for future expeditions to the moon, which plan to use this water ice for everything from life support to rocket fuel. But for many scientists, the big question is, how did all that water ice get there? Well, nobody really knows yet. According to Paul Hain, a planetary scientist at the University of Colorado Boulder, there are 3 main theories for how water originated on the moon. The most obvious theory suggests that the water ice was deposited by asteroid and comet impacts, where it vaporized and eventually made its way to the poles. It's also possible that ionized hydrogen from solar winds binds with oxygen trapped in regolith and is eventually released as vaporized water due to temperature fluctuations on the surface. Finally, there's a possibility that water was present in the material that originally formed the moon and was forced to the surface by volcanic eruptions. It could be that all 3 processes were at work, which makes it a question of how much water each mechanism contributed. Luckily, there has been some promising initial data. In 2009, NASA launched the Lunar Crater Observation and Sensing Satellite on a mission to impact the lunar surface at the South Pole. And this mission not only detected the presence of water, but it also identified a mix of other materials that are common in comets, suggesting at least some of the water hitched a ride on space rocks. To get a better idea of how much of the moon's water was brought to the lunar surface by comets, asteroids, or solar winds, it will be necessary to send a robot or human to take a sample and examine its isotopic composition. That's really the only way we can definitively associate that material with a source. But even if scientists can determine the origins of lunar water, there's still the question of how it came to be concentrated in the poles, a controversial topic, according to Hain. Currently, the lunar science community is divided on whether water that is vaporized during comet and asteroid impacts can travel across the surface of the moon or whether it becomes trapped in the regolith. The only way to know for sure is to return for further tests. One of the biggest questions facing lunar scientists is whether the moon houses alien life. Conspiracies about little green men aside, some scientists believe water stored under the satellite's surface may hold ancient microbes. According to Professor Christopher Palma, an astrophysicist at Penn State, one idea for the origin of life is that its building blocks were delivered by comets. There may be remnants of those in the ice on the moon. Scientists won't know for sure until they send a probe, or human, up to the lunar surface armed with a hefty drill. One enigma that's sprung up only recently has to do with the discovery that something massive is lurking underneath the south pole of the moon, below the largest impact crater ever made in the entire solar system. Scientists have no idea what it could be, but it's certainly big enough to affect the gravitational force exerted by the moon's mass. Predominant theories suggest it's some sort of heavy metal body from a projectile that impacted the surface a long time ago. But this is far from certain. And it's hard to understand what this mass is doing suspended underground. We know the moon's interior is still active to some degree, and heat should have caused this mass to shift around instead of staying trapped like Han Solo in carbonite. Put simply, the moon, once again, raises questions we're just not able to answer yet. Another stunning revelation showed there are earthquakes happening on the moon pretty frequently, otherwise known as moonquakes. Apollo-era seismometers installed on the surface measured these shakes from 1969 to 1977. That data has shown us that the moon is an active body, a far cry from the stale, lifeless rock many assume it is. We're already aware of a few phenomena that cause these quakes, like thermal expansion, tidal stress induced by Earth's gravity, and meteorite impacts. But with such limited data, we're not entirely sure how these processes work and exactly how the quakes behave. Moreover, there are other, shallower moonquakes without any obvious cause, which seem to be occurring more recently than the others. Petro suggests a global seismic network installed around the moon would be tremendously helpful in helping understand the trigger mechanisms behind all this tectonic activity. Such a network could cleanly identify exactly when these events occurred, where they originated from, and the effect they have on the rest of the moon. The 50-year-old data we're using now won't be enough to give us any good answers. In addition, scientists also believe that there's a reason we've only ever seen one side of the moon. It's tidally locked, which means only one side of it faces Earth. This is not uncommon for moons in our solar system, but it's still unclear exactly when this occurs, what conditions encourage it, and how it happens. So, in some scientists' mind, this mystery of tidal locking harkens back to the question of the origin of the moon and what was happening in early lunar history. It's another piece of the 4-billion-year puzzle. What's more, this mystery isn't just local to the moon either. As we continue to find more planets and moons outside of our solar system, it's important to figure out what sort of factors help incite features like tidal locking and decide whether potentially habitable worlds, like the TRAPPIST-1 exoplanets, really are hospitable to life. After all, if scientists can lift the veil on moon mysteries, we could have a better understanding of the solar system's history. The moon lacks much in the way of an atmosphere and hasn't been volcanically active for billions of years, which means its surface has remained relatively unchanged across the eons. In this sense, says Prabal Saxena, a postdoctoral researcher at NASA's Goddard Flight Center, the craters are like the pages of a history book of the early solar system, if only we could figure out how to read them. As mentioned previously, a prevalent theory of lunar formation says that our planetary neighbor was bombarded by space rocks about 3.9 billion years ago. If the samples from the surface confirm that there was a lunar cataclysm, this could also tell us a great deal about how the solar system formed. Not only would it suggest that the outer planets were once much closer to the Sun, it would likely mean that the Earth was bombarded too. This would have vaporized any water on the Earth's surface and killed any life that may have existed there. Strangely enough, the Moon also appears to have recorded early solar history. Just a few years ago, Saxena and his colleagues used the composition of the lunar crust to determine that our Sun likely rotated 50% slower than similar newborn stars during its first billion years of life. The Moon and Earth are largely composed of similar materials, but the Moon has notably less sodium and potassium. Using this evidence, Saxena and his colleagues ran simulations that showed how solar activity can either deposit or strip the Moon of these minerals, and then incorporated data about the relationship between solar flares and stellar rotation rates. According to the simulations, the Sun must have been rotating slowly to account for the levels of potassium and sodium observed on the Moon today. This data about the Sun's early history can also help explain things like how quickly Venus lost its water, how quickly Mars lost its atmosphere, and how it impacted atmospheric chemistry on Earth. As NASA and other space agencies lay the foundations for a permanent human presence on the Moon, there will be more big questions to answer, and the Moon is really just a small step toward the giant leap of unraveling the origin of everything we know. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.